Okay, welcome back, everybody. Sorry I was a little bit late today. Bunch of meetings. Okay. Um, Hope you had a nice weekend. So the plan for this week is we want to finish obviously the front end. There's still quite few things to discuss. And then once we finish this, we're going to start talking about branch prediction. My hope is that we can start talking about branch prediction a little bit today. And then, as I told you, the CA1, the first computer assignment, will be based on branch prediction. And we're going to hopefully release it next Friday. And it's going to be actually, we're going to follow along the rules of the competition, the live competition that's happening right now. And you may or may not want to participate in the competition, but we're gonna like follow the rules. But it's like a very nice kind of, the timelines kind of match pretty well with the competition as well. So probably gonna be able to, some of you who are interested, wouldn't be able to participate at that one as well. One more thing is that unfortunately I have a bunch of travel this quarter. I managed to kind of put them in days that it's not overlapping with the class. But this Wednesday, we won't have in-person class. So I'm gonna just publish a video for the branch prediction. So this Wednesday particularly, we won't have any class. But this hopefully won't happen more than just this once. So just FYI. I'm gonna release the video for branch prediction, whatever we cover today, plus everything else. So keep an eye on that one. You can watch it whenever you want to watch it, but no class on Wednesday, okay? Any questions? And then we're gonna hopefully clear the wait list sometime this week by Wednesday, hopefully. So everyone who's on the wait list should be able to enroll automatically to the class. Those of you who needs a PTE because of the restriction as an undergrad, I'm gonna just start issuing PTEs also this week. Please reach out to me. And then I'll send you a number, and then you can enroll. Okay. Cool. Any other questions? Are we clear? All right. So if you remember, the last thing we were discussing was fetching. So essentially, fetch, as I said in Boom, is 4 stages. The additional stages mainly were like you essentially just need one stage for fetch. But the other 3 stages were added mainly because we're going to do lots of complicated branch prediction, as we're going to actually talk about this today. A good thing about Boom is that you can actually resolve a bunch of branches at the same time, as we're going to also talk about today. And this is actually, as I said, it's going to be module 3. So as I said, essentially the way that Boom works is that it creates a fetch packet, they call it, which is all the instructions that have been read from the memory. So we usually do 4 instructions. So we put them into the fetch buffer. In the fetch packet, it's not just the instructions. Usually there are a few other things, including like the branch prediction information and valid instructions. Like, for example, if you have this kind of misalignments and then we don't really fetch 4 instructions, but we only have 2 useful instructions, you're going to have like a valid mask saying that, okay, the first 2 instructions are basically, you shouldn't be used by the backend. Typically, we also use the, branch prediction information as well. That, like, we assume that this branch is taken or not taken, and we use PC. The reason for this is that later on, when we want to recover things, we need this information back. So we need to pass this around. So there's a little bit of this information that's passed through the fetch. So it's not just the instruction itself, was a little bit more than you usually pass through the fetch packet. So to kind of remind you, this is where we are right now. We are like doing this 4-stage pipelining thing for the fetch, and then we put everything into this fetch buffer. So let's actually start talking about the code and renaming. So these are the main 2 other things that we need to talk about in our front end. So what is a decode? Decode essentially is I would say the simplest thing that you would do in a processor. All it needs to do is essentially just looking at the instruction and decide what needs to be done. Okay. So there are three main things that needs to be done for a decode. Of course, the very first thing that needs to be done for the decode is what is the instruction, right? What type of instruction is this? This is the ALU operation, this is the branch operation, this is the load operation, and so on. Remember that we had different types, bless you. We had different types of instructions in RISC-V, for example. So it kind of tries to first kind of populate that type and so on and so forth. And since we have usually we have 4 instructions being fetched, you want to also decode that many instructions. Otherwise, this creates a bottleneck, right? So you want to be able to, hopefully if everything goes right, you get you fetch 4, you decode 4, you execute 4, and so on and so forth. In reality, that doesn't usually happen because various different reasons. Already you know that, for example, misprediction or misalignment could reduce your fetch rate from 4 to below 4. We talked about various different cases. But the code is usually it's not creating any sort of uncertainty. So you usually can be able, if you feed it 4, it can produce 4. That's one thing. So once we detect the operation, we also need to decide which sort of resources it's going to need and use, and then the operand. So remember, some of these instructions requires 2 register files to be read. Some of them requires a register file and a memory to be read. Some of them requires a register file and what we call an immediate, which is a number that is already encoded into the system. So the amount of operations required for different instructions might be different. So the decode basically decide that. How do we build a decoder? Decoder essentially is a controller. It's a finite state machine. It's a simple kind of state-based system that based on various different, inputs, it goes to different states. For those of you who are not familiar with this, what is an FSM finite state machine? It's usually a mathematical model of a computation. Usually you have, an input to the system, a state, and then a finite number of states that this state can transition to, right? Usually you transition from one state to another and to another. Sometimes there's a bunch of different options. So for example, for a decode, you can think about it that way, that we have an opcode stage, right? And then based on the opcode, you can go to different stages. So for example, you can go to the add stage, you can go to load word stage, you can go to store word stage, and so on and so forth. And within each, you can have multiple other states. So for example, let's say add, you need to probably read from the register file. So register file states, operation states, and so on and so forth. Depending on basically what your processor going to do, you're going to have a bunch of states. Sometimes you might have multiple. So for example, instead of having an add, maybe you can have what we call an R-type stage. An R-type stage means that this is an ALU operations. It could be add, it could be sub. So in that case, then you're going to have something like add, and then subtract, and so on and so forth. There could be many, right? So there are a bunch of them. So the design of the finite state machine really depends on how you want to do it. What is the main thing in terms of hardware implementation? You want to make this design as simple as possible, because if your decoder becomes so complex, then you cannot finish it in one cycle. Remember that you want to be able to finish your decoding in one cycle. So there is this kind of trade-off between how complicated your decoder should be and how you finish it in one cycle. So it has to be a little bit of design aware, timing aware design. So you don't want to very deep if analysis, because if you have a very deep if analysis, then it takes a lot of time. Okay. One thing that mainly these decoders these days do is that they decode it into 2 stages. So they decode and then decide some operations during the decode stage. But some of these kind of control signals actually created in the execution stage. Okay. So this is 2-step decoding that many systems use. This is actually what we also discussed in my undergrad class, that you don't need to generate all the control signals all at the same time, because it takes a lot of time. You can generate, for example, if you need to read the register file, but you don't necessarily need to know whether this is an add operation or a subtract operation. In the decode stage, you just say that this is an R-type operation. It's just something that you're going to use the ALU. Then when you're actually going to use the ALU, you're going to decide whether this was an add or a sub. So this way you're kind of like moving some of this processing operation to later stages, make your decoder much more lightweight and fast. Okay. And this is kind of like, a very simple way of thinking about a state machine with multiple states. And usually there's a condition from going one to another. For those of you who are actually interested in how the decoder works in Boom, you can actually go and see the code. The code is actually available online, as I said, so you can see that there are a bunch of different operations here. There are a bunch of different inputs to that, control signals, functional units code, debug is this RVC, which is kind of like a code for particular type of instructions and so on and so forth. And as you can see, it basically generates a lot of signals. So is it a branch, is it a JAL, is it a JAL, is it a store, so on and so forth. So this is essentially what it does, and this will obviously translate into an RTL code. So this is not a software code. This will be translated into hardware. You don't want to run this in software because that will be very slow. This is actually going to be translated in software. By the way, Boom is using this language called Chisel, which is kind of like, thinking about it is, for those of you who are familiar with like HDL code, is kind of like System C. It's a little bit even more high level than System C. So it's kind of like formatted like Java. So it's kind of like syntax space. It kind of looks like Java, but it's called Chisel. So it's just kind of like a unique thing for Boom. But this can be then translated into something like Verilog. So it's not Verilog, that's what it is, you can see. So it's a little bit more readable than Verilog. Well, again, if you're interested, you can take a look at Chisel as well. But yeah, so this code is available. You can actually spend some time if you want to play with it. One important thing is, as you can see, for the example here, it's not calling instructions, it's actually called macro ops. So what's the difference between macro ops and instruction is that macro ops are usually smaller granularity of than instruction. Sometimes an instruction can be broken down into smaller micro ops. For RISC-based, for the reduced instruction set, that's typically instruction and macro ops are the same thing. Although it's like some small cases, there is difference between macro op and instruction. So for example, let's say for a branch prediction, you need to do some comparison, and you also need to change the PC, right? So you can basically divide this into a comparison macro op and changing PC macro op kind of thing, okay? But there's a whole bunch of there are a bunch of compressed instruction, unaligned instruction, and so on in RISC-V that requires a little bit more involved macro op operations. For now, you don't really need to be worried that much about macro ops. We're not going to actually go through the details of macro ops, but just know that this exists. Okay. But macro ops is if you go to CISC based like x86, everything is macro ops. So essentially, the notion of instruction is only in front end. In the backend does not understand instructions at all. It's only understand macro ops. So sometimes for some of these complex CISC based instructions, one instruction can be produce 4 different macro ops. Okay. So there's an imbalance between macro ops and instructions, especially for CISC-based operations. All right, so that's it with the decode. Any questions for decode? Yeah.
So in CISC-based systems, if an instruction is always translated to a bunch of micro ops, then why don't we just compile into the micro ops instead? Why do we need the instruction as an abstraction over the micro ops?
So the question is, why do we need instruction as an abstraction to macro ops? So that's generally the whole argument between RISC and CISC. So a good thing about CISC is you can reduce the size of the code. So you can have one instruction that can produce multiple macro ops. Sometimes it can, sometimes it cannot. So you can get a little bit of flexibility in terms of the way that you can write. That's where you can actually make the instructions smaller and bigger. But on the flip side, that creates a lot of complexity in terms of decoding and understanding the code because the size of the instructions might change. So there's pros and cons like this. To be honest, usually the kind of short answer to your question is that we don't. That's why most of the systems are transitioning to a macro op based operation. But like a long time ago when they started designing x86 for various reasons, they decided that they need two abstractions, and that's how they did it. Another good thing about the instruction macro ops is that you can add more macro ops without really changing the ISA. And that is like another big benefit of x86. That underlying, you can, for example, say that, okay, now I want to make multiple macro ops per instruction. Like, I can further divide down, or I can introduce new operations and all that without really going back and changing ISA. Versus for something like RISC-V, that's much harder because you need to then change the ISA, and changing ISA means that you have to change the compiler, you have to recompile the whole thing. So there are a whole bunch of these things that could happen. So that's kind of the main benefit of macro op. Yeah.
Are these micro ops like standardized across different ISAs? Like, is that the reason why like Rosetta works for translation between like x86 programs to ARM programs?
Well, for cross compilation, you don't need necessarily macro ops. You just need to be able to translate instruction to instruction.
Okay.
So that's pretty standard because both of them are based on the standards of the ISA. But yeah, what really happens is that you don't need to go back up to the instruction level. You can actually translate macro ops to macro ops kind of thing, right? So, or instructions to the macro op. So what really happens underneath Rosetta is probably that. I don't know the details, but I'm guessing this would be something like that.
Thank you.
Cool. All right, so let's talk about the third part of the backend, which is the renaming part. So as you can again see that now we are kind of like doing the fetch. We put the things to the fetch buffer. Now we can decode things. Just a reminder that we are using this simplified version of RISC-V that's kind of try to combine things. So decode and most of the decode and some part of the rename happens in one clock cycle. Some part of the rename and dispatching, which would be basically something that we need to do. That is kind of like the transition between backend and frontend, frontend and backend is called dispatching that I'm going to talk about later. So what is the renaming and why do we need it? So first of all, as you can see, the difference between an in-order processor and an out-of-order processor is that in in-order processor, we fetch and decode things in order and execute them in order. For out-of-order processors, we fetch and decode still in order, so nothing really changes. But when we want to execute them, we execute them out of order, okay? Why do we want to do out-of-order execution? Obviously, because we want to keep the execution units as busy as possible, right? So I told you before that, if I have sequence of instructions like this, if for any reason, for example, this instruction is dependent on this instruction, then in in-order execution, unfortunately, everything from here downwards needs to wait until this instruction resolves, so then I can run this instruction and then I can run the rest, right? And if I have many execution units, as you can see, this is a super scalar, very high-end processor. I have all these units that are ready to be executed, but I don't really feed them enough instructions. And here it doesn't matter what is my fetch rate or what is my decode rate, because there is this relationship between this dependency between these instructions that's kind of block everything. So the obvious answer to this question of like, how do we fix this is out-of-order execution, which basically the idea is that, okay, if this instruction, for example, or this instruction has nothing to do with the results of this, I can just basically feed this into my pipeline, right? So what I would do is that then I look at like a larger window. So I fetch more instructions or decode more instructions. I kind of park them into this a stage, this dispatch stage that we're going to talk about it later called reservation station. And basically from here, I'm going to go and pick and choose. For example, say, okay, this guy, this guy, this guy, and this guy, these are, dependent from each other's. So let's pick these four and execute them. So I'm going to run this one, run this one, run this one, run this one, right? And then basically this means that I can now remove them from the reservation station, right? So I'm going to remove this, remove this, remove this, remove this, okay? Then what I do is that from the front end side, I'm going to continuously feed more instructions. So this is where the fetch and decode happens. So I'm going to continuously put more instruction in. So I'm going to put this instruction, this instruction, this instruction, this instruction. Then the backend going to continuously kind of independently search through this instruction and pick another 4 next cycle and pick another 4 next cycle. So as long as this kind of backend front end operation goes hand in hand, and I always have 4 instructions that I can feed through my execution unit, then my cycle per instructions are going to be low, right? They're going to be 4, for example, if I have a 4 superscalar system. My instruction per cycle, in other words, is going to be 4, right? But there are a few challenges that we need to fix in the system. The first one is renaming. So what is renaming? So as I said, this is kind of like how simplified version of the system would work. There are 3 things that we need to fix. One is, first of all, how do we actually do this kind of dependency checking? That's one thing that we're going to do in the dispatch, and we're going to later describe. The second thing that we need to fix is what if we need to recover things? Because if I kind of mix and match instructions and execute things, and if I made a mistake, for example, if I do branch prediction and I realize that I made a mistake with my branch prediction, how should I fix it? I need some complex mechanism to recover things. And thirdly, there is this unique problem called renaming that I'm going to talk about. Okay, so for now, don't worry about this unit here, which is the reservation station, and don't worry about what is this retire thing. Let's actually focus on this other problem called renaming. Okay, so what is the renaming problem? Most of you probably know, but I'm going to just go through it and pretend that you don't know. So we're gonna, as I told you, the main reason that we need out of order execution and the main reason that we need to select instruction is that there is dependencies. So there is what we call a true dependence, or read after write, and that's the major problem in our systems that we need. That's the main reason that we cannot run instructions one after another. So look at this example. I have an add, and later on I have a subtract. And as you can see, the add is x2, x1, x3, and sub is x4, x3, x2. If you're not familiar with syntax of RISC-V, what does this mean is that x2 is equal to x1 plus x3, and this one means that x4 is equal to x3 minus x2. Okay. So what does this mean is that, as you can see, x2 here has this raw data hazard or raw dependency, which means that I'm writing to x2, and later on in some other future cycles, I'm going to read that value and subtract it from x3 and rewrite it to x4. As you can see, if I change the sequence of these 2 instructions, then we're going to lead into correctness issues, right? Because when we are writing our programs, we assume that things happen in order, right? So the programmer does not understand the underlying of an out of order execution. So it's hardware's designer's job to make sure that this order has been preserved. If you want to execute this out of order, you have to make sure that you're not creating these correctness issues. Okay. So I cannot basically reorder these 2 instructions because of these raw data hazards. We call this a true dependence because there is indeed a dependence. But there are actually other sequences that looks like this, but in fact they're not. They're just the way that we are writing the program that cause this dependency that we can fix. This one we cannot fix, but there are the other 2 that we can fix. So what are those? The first one is what we call write after write dependency. Okay, this is called output dependence. So the output dependence looks like this, that essentially you have an add instruction, similar add instruction as previously, and you have another sub instruction. But what happens is that in both cases, x2 in this case, this register number 2, is the destination registers, which means that in this case, x2 is equal to x1 plus x3, and x2 is equal to x3 plus x4. X3 minus x4. So what is happening here? First of all, can I reorder these things? And if I reorder, what happens? Yeah.
In the register table, you're going to have the wrong value for x2.
Yes, you're going to have a wrong value for x2 if I reorder this, because the assumption of the programmer is that at the end of the execution of this, the value that x2 has to get is this value, this updated value. So I don't care about this one, because eventually at this point, I'm going to get this one. But if I reorder them, then x2, the value that x2 has at the end of this program is the value of x1 plus x3, right? But this is not a true dependence, because the easy fix for this would have been, anyone wants to suggest how to easily fix this? Yeah.
Just change the register.
Just change the register, right? Because essentially this is like using the same variable in your code, whereas you can just define a new variable and then as long as you have, some variables that you can assign this, that for example, if I rewrite this code and say that instead of x2, this is x5, then everything is fine. I can then essentially freely change the ordering of this instruction because this one is x3 minus x4 equal to x5. This one is x2, x1, x3. Doesn't matter which one I do first. I can freely reorder them as much as I want. Okay, this is what we call write after write because essentially you're writing to the same register twice, but it's not a true dependency. It's called output dependence. So I can actually reorder them if I fix the problem. And lastly, I have this write after read. This is called anti-dependence. So I have a scenario like add x3, x1, x2, and then sub x2, x3, x4. Can I reorder this? Yes or no? No, right? Because again, if I reorder this, I'm updating the value of x2 and then gonna use it to add x1 to it. Whereas in the original program, initially the programmer thought that this x2 is not updated here. So you're kind of like updating it with the future value and using it in previous values, and that's definitely going to cause problems. So I cannot, as is, change this. But any suggestions on how to fix this? Anyone? Yeah.
Also just like change the output register on the second one.
Yeah. If I change this to x5, then I can reorder them easily because again, this is not so whether or not I run this before this or this, that shouldn't change this value, right? So I can then run these completely separate from. Although here we have another problem, which is this x3 and this x3. So just be careful of that. But maybe if I do this, then we should be okay to move things as I wish, right?
For both of those hazards, do we also need to eventually set x2 to x5 again later or no?
So the question, well, no. So this we can actually do this during the compile time, or as we're going to show it during the renaming stage. So there will be actually a mechanism of how do these things on the fly, so dynamically. So essentially, kind of the basic idea going to be that we're going to issue some IDs, and then you're going to play with those IDs. Okay. All right. So as you can see, if I change this, then I'm going to fix this issue with no problem. So these two is called these. So first one, I cannot do anything about it. And the way that we're going to fix this is that, as I said, we're going to increase the window size and bring more instructions. And hopefully there is enough independent instructions that I can keep my pipeline going. Although this is not guaranteed, and that's why we're never going to get like always IPC equal to 4 in our design. But hopefully we can get very close to it. But the other two we should fix, and these two are quite common. So we don't want this to happen. Of course, again, I can keep these as is and say that, okay, these are all dependencies, and we're gonna actually like increase our fetch rate even further. But in reality, it shows that it's better to actually fix these issues before actually feeding it into the reservation station. Yeah.
So in the last example, if we look at register x3, we actually have a raw dependency.
Yes.
Right?
Yes. We do have raw dependency. So essentially, as I said, you have to be careful about that. I think it was a bad example in terms of like probably this should have been x6 so that to make that issue gone. Yeah. All right. So why do we have this false dependency in the first place? Why are we using this like x2 here? Why don't we like just use x5 to begin with? The problem here arises from the fact that we have limited number of registers in an ISA. So usually, for example, for RISC-V, you only have 32 registers, okay? And many of these registers, if you're familiar with like caller and colleague, there are a certain number of rules that you have to use when you're calling a function and returning from a function. So it's not like you can use all of these registers. Some of them are reserved for certain things. So for example, one is reserved as a stack pointer. one is reserved for return address, one is reserved for return values, and so on and so forth. So there's usually at any given point, there's 8 to 16 registers that you can really play with. These are temporary registers, okay? And when you're writing the program, it's very common that very soon you're going to run out of these registers. That's why the compiler has nothing to do, like it has no option but to reuse some of these registers. Imagine that you have to only has 8 different variables in a large C code, and they ask you to write a code with these only 8 variables. At some point, you're going to use these variables, multiple times, okay? And then another reason that you're going to have this is like, reusing the actual code, right? So for example, if I write a code in a loop, I'm going to use the same registers over and over. I cannot like change that code because this is the same code. I just reuse it and rerun it over and over. So there are scenarios that even if I have infinite number of registers, I'm going to still have this reusing problem. I can, for example, unroll the loop and then assign different variables for different body of the loop. But again, there are some other problems with it. It's going to bloat your code because unrolling the loop means that there are more instructions and all. But in some cases, you can do that. But typically, the bottom line is that I need a mechanism to fix this issue on the fly during the execution. Okay. So as I said, raw data hazard we cannot fix, but the other hazards we can fix it with renaming. So what is renaming? So essentially the idea of renaming is this very fundamental idea that you have limited architectural registers. These are your X1 or X0 to X35 in RISC-V. But in reality, you can have many, many more what we call physical registers, okay? So I can build a very big register files with 1,000 registers, okay? If I have space and if I'm able to, pay and afford the power overhead and the area overhead, nothing actually limit me from having bigger physical registers. In fact, most of our modern processors has 256 registers and so on and so forth, okay? So in order to distinguish between these two registers, we call one AREG or architectural registers and the other one PREG or physical registers, okay? So first of all, why can't I just have one physical register? What's limiting me from, why do I need to maintain this architectural registers? Anyone wants to answer that? Yeah.
The ISA spec is fixed.
Yeah, so the ISA specs is frozen. So it's not like, oh, tomorrow I want to add more registers to the system, because if I want to add more registers, then I need to basically go and change the ISA. Because remember, in the ISA, there was like units that kind of define RS1 and RS2 and so on and so forth. And there were a limited number of bits assigned to them. For example, for RISC-V, there are 5 bits for RS1, which is the register source 1, and 5 bits for RS2, which means that at most I can have 32, right? With 5 bits, I can represent 32 different numbers. So it's not like, oh, tomorrow I decide that I need 1,000, because for 1,000, then I need 10 bits for this one and 10 bits for that one. And that means that I now need to change my ISA, and the ISA changing is a no-no, right? So that's why I need to stick to this 5.5, but then I can decouple it with the physical register. So now I need to find a mapping mechanism that can map an architectural register, one architectural register to multiple physical registers, okay? So this way I'm going to fix this issue of limited number of architecture registers. This will also fix the issue of renaming, because remember that I have this issue that now there was X2. So if I pretend that these are my architecture registers, then one time I can assign, let's say, P5, and one time I can assign P7 or whatever. I'm just making up numbers, but I can assign for this instruction, I can assign P5. For this instruction, I can assign P7, and great, everything will work out after that. Right, so that's the basic idea of renaming. So what do we need for this? We need 3 things. We need a mapping mechanism. We need, of course, physical registers. For physical registers, we need a mechanism to know which one is assigned to what, which one is free and available, and which one is already allocated, because you cannot like double allocate, right? And then you need an allocation and deallocation mechanism, because if I don't deallocate, then after some time I'm going to run out, right? So once the instruction is finished, there's no reason to keep track of that physical register anymore. So I can deallocate it and put it back into what we call a free pool. And then the third and very important thing is that I need a state maintenance. Why? Because again, if I do this mapping and later on realize that I need to revert and need to go back because, for example, I have a branch misprediction. So I need to kind of like recover the system. I need to also recover my mapping because I keep, map new things and then at some point said, okay, these 10 instructions, I need to get rid of them. So I also need to revert back their mapping. So there are 3 things that I need for my renaming strategy, okay? So how do we do that? There are actually 2 ways of doing this. The ones that I'm going to explain here is what we call a RAT strategy. So there is this thing called register alias table or RAT. What a RAT does is that think about it as it has 1 entry per architecture registers. So for example, for RISC-V32, we're going to have 32 rows. Each row has basically this one is x0, this one is x1, and so on until x33. And then for each one, we're going to basically maintain a register, which is the current mapping between the architectural register and the physical register. Okay. So we're going to basically the RAT gonna basically remember the most recent mapping of the 2. Then we also need to remember the previous mappings. In order to remember the previous mapping, either I can basically add new columns here and basically kind of like maintain multiple mappings, but typically we pass that part into what we call a reorder buffer, and that's where we're going to store that. But for now, just remember that the RAT is basically just remember the latest mapping, okay? And then we're going to basically, what we're going to do is that there is a simple algorithm for this, that whenever we see an areg, we're going to go through this pool of available registers and map a new one to the areg, and then remove that from the free pool. Whenever the instruction is done, we bring that register back into the free pool. So that's kind of like a very simple algorithm that we're gonna do this. This is an example that I provided in my undergrad class. I'm gonna actually repeat it here so that you can kind of understand the basics and mechanics of this rack. But as I said, there's another approach that you can also use for this using scoreboarding and this two-muscle algorithms. In fact, that's actually what you're going to use in your project. So this is slightly different than that. Later on, we're going to discuss that as well. So let's say, for example, we have 5 architectural registers. This is a toy example. And then let's say we have 10 physical registers. Okay, so I'm going to show them as P0 to P9. And then architecture register, actually, I'm going to show it as P1 to P10. And then architecture registers, I'm going to show them as X1 to X5, okay? So let's say, for example, there is an initial mapping. Again, this is an example, just this initial mapping that, for example, initially X1 is mapped to P1, X2 is mapped to P2, X3 is mapped to P3, 4 to 4, 5 to 5. That means that I have 5 physical registers that are not assigned to anything. I put them in the free pool, okay? So here's the renaming algorithm. So let's say I have these 4 different instructions. I'm going to rename them as we move forward. The algorithm for renaming is this, that remember that the thing that we want to change is the destination register, right? So I don't want to rename the physical register, the source register, because this is the input to my system. What I want to rename is the output. So here's what we're going to do. So we're going to take an instruction, okay? And we're going to look into the table for these source instructions and see whatever mapping they have, we're going to use that. So X1 is mapped to P1, and X2 is mapped to P2. So I'm going to say OR, and then I'm going to do P2 and P1. And now I need to decide what do we want to do with the source destination register. As I said, we want to find a new mapping. For every new destination, we create a new mapping, okay? So X3 used to be mapped to P3, but now since I want to have a new mapping, I'm going to go through the free pool and pick one register and assign it to X3. How do I pick that? It could be like from the top, from the bottom, could be random, whatever. But let's say, for example, I pick P6 here, okay? So basically, my new mapped register is P6. What I need to do is that in the RAT also needs to kind of like show this as a new mapping. Remember that we usually need to remember the old mapping as well, because if something happens, we need to be able to revert it back. We usually put that into my ROB, but you can also like put this into another column of this rat as well. Another thing that I need to do is that I need to remove this P6 from the free pool because I don't want the next instruction to also assign to P6 because P6 is now in use. Okay. So here's the steps. I do these things. I put P6 here. P6 is removed here. So I'm going to continue the next one. So now I have add x4, x3, x4. So I do add here. I look at x4. I see P4. I put P4 here. I look at x3. I'll see P6. Just be careful that you look at the most recent one. So I put P6 here. Now I need to change x4, and then x4 needs to be a new mapping. So it used to be P4. Now I pick P7 and put it here. A few things to remember here is that, as you can see, x4 here is both source and destination, but we do it from this way on, right? So we use the previous source, which in this case it was P4, but the destination is P7, okay? And another interesting thing is, as you can see, there is an x3 here and x3 here. And as you can see, there is actually their physical reducer is also preserved. So the true raw dependency, this was the true raw dependency that we have. We still maintain that. We're not making any problem with that. So that's great. But later on, you're going to see that, for example, we have x3 here and x3 here. And you're going to see that we fixed that issue later on. Any questions so far?
Have we ignored deallocation for now?
Yeah. So for now, I'm just renaming. There will be at some point that this instruction is finished, and we need to define formally what is a finish because we still haven't talked about the backend. But once we talked about the backend, there will be a stage that we call this retire. That's when we absolutely ensure that this instruction is no longer going to be used. That's when we're going to deallocate. But now we're not going to deallocate P7, we're going to deallocate the previous mapping. And again, later on, we're going to describe why we need to deallocate the previous mapping, not the current mapping. Yeah.
I'm a little confused for how it would work in the mapping for x4 being in the source and destination. group. Like if you're mapping it to P7 instead of P4, but.
You can also map it to P4. But remember, it always wants to change the destination to a new one so that it doesn't have the unnecessary output dependency to the previous instructions.
Right, I guess what I'm confused in is if we change the output dependency. Will that cause issues with the source also being the same register?
So basically what happens is that from this point to the past, we're gonna use P4. Right, so we're always going to use P4 wherever we see it here. From this point on, we're going to use P7, right? So at this point, P4 and P7 is going to be essentially similar, not similar things. It's going to be basically P7 is P4 plus P6.
Right.
But from here on, if I see X4, I'm going to use P7. So it's not going to introduce new problems because essentially I could have said P4 and then continue P4. That could have worked as well. The reason I'm using P7 is that now I'm decoupling P7 from P4. So for example, if I have a P4 here somewhere, then I can safely, reorganize this, assuming that there's no raw data hazard, right? All right. So that's it. P7, we remove P7 from here. Let's actually do this yourself. So let's do solve x3, x5, x2. Here's the table. Anyone wants to say what should we put? Yes.
P8, P5, P3.
P8, P5, P2. Anyone wondering why? Good. So yeah, we changed the mapping of X3, and as you can see, X3 has been mapped twice, right? So one time is P8, one time is P6. And then you can see that if I didn't have this instruction, for now, let's assume that we didn't have this instruction. If we only had these two instructions, you can see that one is sub P8, P5, P2, the other one is P6, P2, P1. I can now freely move them around because they are just separate instructions, right? So that's what's renaming going to give you. Of course, in this particular example, I cannot move this up because of the dependencies between the X3 here and X3 here. But other than that, you could have done it, right? Any questions? Okay, cool. And then the last instruction, do this as well. Yeah.
P9, P2.
P9, P what?
P8.
P8, and 2, right? So this is add I. This is so as I said, when you say this I, it means that it has this immediate values, which in this case is a 2. 2 is not a register, it's just a number that is embedded already in the instructions. So we don't need to rename immediates, you just use them as is, and then you continue that way. Yeah.
Why should we remap the X1 even like because it was P1? Why are we doing that? We don't know the next instruction. Is there any reason for
Well, there will be next instructions. There is always next instructions.
So we always try to remap.
You always remap the destination registers no matter what. Yes. And then I'm just showing you a toy example, but yeah, it's always going to be next. Yeah.
So don't we run out of free registers pretty quickly?
Good questions. We might run out of free registers. So first of all, here I'm just showing you 32 to like a 2 to 1 mapping, but in reality it's usually 32 to 128. But also keep in mind that these instructions also finish so fast. So by the time we reach to here, this first instruction is going to be executed. Because any instructions is like somewhere between 8 to 10 cycles within the pipeline, hopefully, right? Otherwise, we're not going to get good performance. So really what you need is being able to have that 8 instructions kind of in, right? And then this is super scalar, so it's like a little bit more, but still we're going to have a lot of registers. So we're usually good. But what if that we run out of instructions? What would happen if we indeed run out of instructions? Some weird cases we might. In that case, we're going to stall the backend. Stall the front end. So we're going to continue, let the backend to continue, but we're not going to fetch new instructions. We're going to stall it. We're not going to rename new instructions because we don't have enough instructions. At some point, since the backend is going to continue executing, some of these instructions will be finished, and we're going to put back things into the free pool, and then at that point, we're going to continue.
So what determines if we can put it back into the free pool?
So essentially, there will be, what determines if we can put it back? Yeah, once the instruction is finished, so for example, once this OR instruction, so if I go back to the pipeline, where's our pipeline? Way up. Okay, so as you can see, there is this second part to the system, which is the backend, right? So the instruction is going to be renamed at this position, and then they're going to continue and going to get executed. At some point, it's going to get finalized, okay? So here we're going to send back commands to our register file and to our decoding logic that this instruction is finished. Free it, okay? So it's going to free this, and then when we are doing the renaming, we're going to see that now the new registers pops up, and then we're going to continue. But the way it's going to work is that we're going to freeze this part, but we're going to let this part go. If we freeze everything, then we're going to be at deadlock, right? So we're going to let this backend goes, but the front end is going to be frozen. But very, very rarely happens because essentially we're going to have, that's actually the main thing about, this high-end processor, you're going to have lots of registers because of this. All right. Okay, so as I said, this is one algorithm for doing this, and this is usually what we do with the renaming. But as I said, there are generally 2 ways to do renaming. There is an explicit way to do renaming using a physical register file, And this is what Boomi does. And there's another thing called implicit renaming, or this is called data in ROB. And that's another way of doing this. So let me actually give you a little bit more kind of like a design for this. So first of all, ROB is this thing called reorder buffer. Essentially, the way that this reorder buffer works is that later on when we want to do recovery, you're going to see that this is very important. Or now just know that during the decode phase, since we want to remember the correct sequence of the program, once we fetch the instructions, we're going to basically reserve a spot in our reorder buffer. So essentially, our reorder buffer is the sequence of instructions that do actually come from the order of the program. We're going to execute them out of order, but then we're going to kind of put them back in order. The reorder buffer allows you to kind of execute things out of order, but when you actually wants to complete them and retire them, you retire them in order, okay? So what's the difference? But then it's going to be, there will be some discussions about reorder buffer yet later when we are discussing about the backend, because technically reorder is part of the backend. But for now, let's talk about the implicit versus explicit renaming, okay? So the way that the implicit versus explicit works is that the fetch is the same. We're going to have a fetch buffer in both cases, and you're going to have multiple instructions, like 4 instructions. Then you're going to have your decode and rename logic, as we explained. In the explicit one, what you're going to do is that you're going to actually have a physical register file right before the execution unit, okay? So what you're going to do is that you're basically going to just have the names of, the register names, the register numbers. And then when you actually want to execute them, you're going to go and actually grab the values. So for example, like I told you that, like, in this table, I have like P9, P2, P8, and so on and so forth. These are not values, right? These are just register names. Each of these registers has this explicit value, right? So for example, it could be a 64-bit number or it could be a 32-bit number. So the way it works is that I don't necessarily need to pass in and read the values right off the bat during the decode. I can just pass on the register names. And during the actual execution, right before I want to actually, let's say, add these 2 numbers, I'm going to go and grab the value for P9. I'm going to go grab the value for P8 and execute this. Okay? So this is one way of doing this. So essentially what we do is that during the decode, we just put the instruction names, and then in the reservation station, we're going to just put the register numbers. You can treat this as some tags, right? So for example, P1, P2, I can use this type of tags, or I can actually assign different tags, okay? So this is one way of doing this. The second way of doing this is that actually this might be like, people might say, okay, this is confusing. Let's actually, like, whenever we want to rename, let's actually read the actual values and put it into my ROB as well, okay? So this is what we call data in ROB, which means that whenever I'm decoding, I'm not saying, oh, P8 or P7. I'm going to actually go and read the register file and put the value into my ROB, okay? This way, when I want to execute this instruction, I can basically right away execute it because I already have the numbers, okay? So there are 2, and again, we're going to revisit this when we are talking about the execution unit and when we are talking about the register file. But generally, as you can see, the difference between these 2 is that, in this case, we're going to basically access a physical register file, PRF. In this case, you're essentially just accessing an architecture register file, because at any given point, you see X0, X1, X2. So you're not like populating those like P1, P2. You basically just put the data explicitly into the ROB. So what are the pros and cons of this? So first of all, the one that you use one unified physical register file is called explicit, because you're explicitly accessing the physical one. That's what we explained in the example that I gave you. So we're going to have a map table to keep track of the instructions. For each instructions, essentially we have this. The main thing with this approach is that for each branch, we need to create a copy of this map tables, because essentially after each branch, if I want to recover, this, what I can do is that when I see a branch, I create a copy of this. Then if I decide that, oh, I made a mistake, I go back to the one that prior to the branch. So I can basically have copy of this table, and then just make a lot of copies of this for each branch, and then recover the one that I want. Okay. So for the explicit, I can do this easily. And then on the misprediction or recovery, all I need to do is that find the correct table and copy it there, and boom, we're good, right? So for example, in this example that I gave you, let's say all these 4 instructions that we did was a mistake because, for example, there was a branch that was turned out to be misprediction. All I can do, this is my final table, right? All I can do is that just discard this and go back to the original table that I had, right? So the original table that I have was here, right? So I can, for example, and then I can even have a copy of the free pool, and then I can also recover the free pool, right? So the main overhead of this is that I need to maintain multiple copies of the free pool and multiple copies of RAT, but that gives me instant speed because then all I need to do is just copy this, right? Of course, there will be some limit to this. Usually, this is what we call the branch depth, because I cannot have unlimited copies, right? Because this will be stored somewhere, and that storage might be limited. But usually, high-end processors can go really deep, so like 8 or 16, nested branches. So you can have 16 copies of this at any given time. And once the branch is resolved, then I can get rid of that table. So I don't need to maintain that table forever. Once I know that I make a correct decision about my branch, I just get rid of that table because I no longer need to recover to that point. Okay? All right, so let's have a quick break, then I'm going to talk about the implicit.
Be on top of like. Not worry about
Okay.
this one.
So this is explicit. Let's actually also talk about implicit. So as I said, the mechanism for explicit recovery is that, let's say you have like a sequence of instructions like this. Let's say you have a branch, like a blue branch, you have a pink branch, a green branch, another orange branch, and you have rats. So what you're going to do is that you're going to have copies of this rat whenever you see a branch, right? So you have a blue rat, then you have this another rat, and another rat, and another rat. What you do is that you basically flush the wrong path. You deallocate the rat checkpoints, recover the ones that you want. So for example, let's say this branch is the one that's caused a misprediction. You get rid of everything, and then you go back here and start with the blue rat again. Okay. So and then you continue from the wrong path, from the right path. Yeah.
Sorry, what does RAT stand for?
It's a register allocation table. Yeah.
That was alias.
Sorry, register alias table.
What was ROM?
Reorder buffer. Mm-hmm. So what are the challenges? Of course, again, as I said before, any decision that we make has pros and cons. So there's like no real winner in many of these systems. So the problem with this approach is that I need one checkpoint per branch. And then if I have many branches, this means that, at some point I'm going to get rid of, run out of this copies. And then, for example, if the code is all branches, then essentially means that, essentially all I'm doing is like creating checkpoints. And then if I run out of this, then I need to stall the front end and then let the branches to be resolved, and then I can continue. One solution that has been looked at is that I don't need to keep a copy for everything. I can actually have checkpoints for only low confidence branches. The trade-off with this is that then if I make a mistake, I need to go back 2 or multiple checkpoints back because I don't have a proper checkpoint for this one. I need to revert to, let's say, 2 back. So for example, let's say in this case, if I don't want to take branches for every single, if I don't want to get checkpoints for every single branch, one approach is I only have checkpoint for this one, and not for this one and this one. So what happens is that if I decided that if I realize that I made a mistake here, then since I don't have a checkpoint for this, I need to revert to this one. So it means that I need to rerun a bunch of instructions. But the good thing about this is that if this is a very, very high confidence branch, it's going to very, very rarely happen. So in most cases, I'm not going to make a mistake. So if I'm very confident about my prediction, I don't need to have a checkpoint for it. And still, this doesn't create a correctness issue because I still have like, you know, a plan B to fall back on. But that means that I'm wasting few cycles between the two checkpoints. Okay. But I can, you know, again, to make things simplified, I can just take a checkpoint for every single branch, and that way I can move forward. Okay. But as you can see, that's the story of computer architecture is adding this, packing these features one after another to the system, right? So we initially start with like, okay, let's actually have a rat, but then we say, okay, if you want to branch, what should I do? And then we introduce this additional getting a checkpoint. But now I'm saying that, okay, if I want to be very greedy and be able to, like, you know, satisfy a lot of branches, how can I do? And then I introduce this in another check. So this is, we can quickly see how complicated these systems become. And again, modern processors is all about these very complex features. It gives us a lot of performance, but unfortunately, it's also a lot of power, performance, lots of implementation complexity, and so on, which at the end of the day, that's caused the security issues that we're going to later talk about. Okay, so implicit, essentially the idea of implicit is that let's not have that problem. Let's put everything in my ROB, because ROB is going to be there anyway. I'm going to just extend it with storing the data. Then the good thing is that I only need one mapping. And then when there is a branch misprediction, all I need to do is that basically discarding instructions from the ROB. I don't need to keep copies and things like that. I can just move forward with my instructions. I put them as they come. I keep the data. If I see that there is an instruction, there's a misprediction, I basically just get rid of that instructions. And then that also makes my my execution quite fast, because essentially I've read the data here. Then all I need to do is basically just issue that, as we're going to later on discuss. So the issue windows becomes also a little bit more relaxed and easier. Okay. So what is the pros and cons for this? The pros and cons for this is, anyone actually wants to suggest the pros and cons before I say it? I already said the pros. What is the con? Yeah.
I feel like there's a lot of data movement, like you're passing so much data across like your wires, so it's probably taking like a lot more power.
Exactly. So you're kind of like passing a lot of things. So because initially I just passing the tag, which was usually much smaller, but now kind of read the data early on and then continuously passing that. So essentially, if you look at the kind of in terms of the overhead, I need the data here, I need the data here, and I'll need to also pass this data. Versus for the explicit, I didn't need the data in any of those places, right? So if I go back, as you can see, here things are very lean, right? I only pass tags, and only at this point I'm really reading the actual value. So in terms of storing things, I store much less with the explicit. I also pass less, right? But the mechanism for recovery is much more complex, right? So, and then I need to potentially store a lot of more things at some point. If I have lots of branches, then this may not work very well, right? So that's kind of like the trade-off between these two approaches. Boom is using this one. The explicit approach. Many of the modern processors does that actually. So there's a slight edge over the explicit versus the implicit. But I think many of the Intel processors actually still using implicit. Yeah.
Is there any kind of like hybrid potential where, like, for example, for instructions that like might be more error prone, you use like the implicit approach, or vice versa?
Essentially the hybrid approach was kind of like the one that I mentioned, that you don't take the checkpoint. So if you're kind of fairly confident about your branch prediction, then you don't take a checkpoint, and that significantly, reduce the power overhead for the explicit. But also keep in mind that since these are hardware approaches, you need to put in the functionality in the hardware anyway. So whether or not you use it, that's a separate story. But the main cost of these things is not using them, it's actually putting the features on, right? So for example, if I want to create both explicit and implicit, I need to design some wires and then some ports, and then design storage for it and all that. And typically designing this, engineering design of this is the complex part of any processor. Whether or not I'm using that few bits, that doesn't really matter in many systems. But yeah, you can, for example, have both and then turn it on and turn it off. And that's actually many of these hardware features of these modern processors, they're all baked in. And then they actually kind of, there is a software method that switch it on and off. So for example, when you like, upgrade your system, there's no new hardware being installed in your system. They just turn on the features. So all of the features are already in many of the systems. So for example, any of these multi-core processors that you buy, they're actually having in real world, they have more cores than you buy. But then if you pay more, they're gonna just activate those cores. So like you're really buying an 8-core, but in fact it's functioning only 4 cores because you pay less. So that's kind of like the idea. Okay. All right, so going back here, so this is the implicit, as I said, so implicit versus explicit. So how do we actually implement this in Boom, in renaming in Boom? So an instruction comes, it goes to the map table. As you can see, we have a bunch of instructions, so we have multiple map tables, obviously. Then a whole bunch of things happening. You can actually take a look at it if you want to, but like a big thing that is important is this free list. Somebody asked, like, how do we actually do the free list? There are a whole bunch of signals that are coming back from there to here, and then that's where you're gonna actually, like, create things. And then there's a whole bunch of like, if this instruction is load store, should we do something? If not, and so on and so forth. So there's a whole bunch of details for Boom core that if you're interested, you can take a look. We don't have much time, so I'm gonna basically skip through them. But as I said, they have a very nice documentation of explaining these signals. You can always also go and take a look at their code to fully understand every single block here. So you can actually, if you're curious about the real implementations, you can take a look at those as well. Okay. But to give you kind of like, a quick overview, essentially they have this busy table. That this busy table is keeping this free list table, this table here that keeps track of which instruction is busy, which register is busy or not, and then if they are ready, then they're gonna let it go. The free list keeps track of the registers, an unused one. It's implemented as a bit vector, so essentially the values here are just zeros and ones. That's all you need to keep track of. And then there is some form of a priority decoder to find the first 3 register. So you can, as I said, you can either start from the top, you can use some form of a decoder here. And then, as I said, since this is an explicit method, for every branch, you take a snapshot of the registers, you copy it, and then you move forward. If you detect any misprediction, you zero it out, you replace it with the good known models, and you move forward. Again, there's like lots of logics involved that if you're interested, take a look at the description of the design. Okay. Yeah, and then recovery, as I said, usually we have a map table, the committed map table. This is the correct current table. This is so this one is basically keep track of the actual instructions that are done. So when the instruction is done, we call it commit. So this committed table is the one that is kind of like the ground truth for us. So whenever we see a misprediction and we want to copy things, we copy things from this committed map table into our current map table. So, and then we keep track of this committed map table. Okay. When do we free? When the instructions are done. And again, we're going to talk about this later when we are talking about the destination registers. All right, so going back to this design, this is our simplified design now. So this is fetch 4 cycles, decode and rename. As you can see, we put things into the ROB. Here we only have the tags for now. And then we go to the rename and dispatch stage. At this point, we kind of rename the instructions. We know the source and destinations. There are going to be some logic involved here that kind of read the register, that then going to put it into some form of a queue. This queue is going to be part of what we call the issue logic to choose which instruction unit to use. there are two options for this that we're gonna discuss later. They're gonna be centralized and paired design. So as you can see, this one is divided. So for example, there's a floating point issue queue, there's an ALU issue queue, there's a memory issue queue, and so on and so forth. So we're gonna put these rename instructions here. We're gonna read it from the physical registers and then execute it in our functional units. As you can see, there are a whole bunch of functional units. There is like ALU, multiplication, division, floating points, so on and so forth. There's also multiple copies of functional units because this is again a high-end processor, so it needs to run things fast. So this part on, we're gonna talk about it in a separate lecture when we were talking about the backend of the processor. Okay. So after this, we're gonna talk a little bit about branch prediction. We have a little bit of time today. We're gonna start that discussion. And then later on, we're going to talk about the backend, which is the execution unit. Before that, we're going to kind of have a small pivot and start talking about caches and security. So next week, we're not going to talk about execution engine. We're going to talk about security of caches and cache side channels attacks because we want to introduce the security concepts a little bit faster. But then later on, the week after, we're going to come back and talk about the execution units as well. Okay. Any questions so far? All right, so let me quickly pull up my branch prediction slides. All right. All right. So we're back here. Remember that we go this way and we didn't talk about this part, the branch prediction. So we're gonna actually go back to the fetch again and talk about branch prediction. So again, this is the kind of the internals of the fetch unit. As you can see, a lot of it is actually the branch. So the main thing is this very long 4-cycle branch predictor. In terminology of RISC-V, they call it backing predictor. That is combination of a bunch of different predictors like a G-shear and a tape and so on and so forth that we're going to talk about. But the branch predictor in RISC-V and generally in any high-end processors is not just one thing. There's a collection of things. So as you can see, there's also a branch target buffer or BTB in addition to the branch predictor. So usually like you use this combination. And even in the BTB, you can see that there's actually a bin. It's a bimodal as a simple predictor. And there's also this thing called RAS, which is the return address stack, which kind of like also try to predict, but predict only for return instructions. So there are a whole bunch of things that you need to use. And as I said, branch prediction is very, very important for good performance of the processor, because if you continuously make mistakes, then you already see that's how costly it is, because I need to recover and need to throw out a lot of things and replace it and so on and so forth. Okay. As you can see, the branch predictors continuously gets more sophisticated in versions of Bloom. So initially it was only like a BTB in version 1, only 2 cycles. Then they introduced a G-shear, and the version 3 that we are looking at is also introducing the tape in addition to the G-shear. So what are the main things, what are the main objectives of a branch predictor? There are two things. The first one is that you want to keep the fetch rate as high as possible, right? With the branch predictor, you can basically quickly predict the next instructions and bring it as fast as possible. And you need an accurate branch predictor. So it's not just about prediction, but it's also about accurate prediction. Because if you continuously make incorrect decisions, then you need to flush things, and flushing is very, very costly. And of course, also important is that you need a mechanism for fast recovery. This is kind of not the job of the branch prediction, it's the job of the pipeline itself. And then branch predictors are very, very accurate these days. So we're talking about 90-something% accuracy. So branches are really, really accurate. So that's very important for a high-end processor. Okay. All right, so what are the two things that a branch predictor needs to do? Branch predictor needs to basically decide and provide answer to two fundamental questions. The first one is the direction of the branch, whether this branch is taken or not taken. We're only talking about binary branches, so either the branch is taken or the branch is not taken. If the branch is not taken, essentially what it means that if I have my instructions and this one is a branch, if the branch is not taken, I'm just going to continue, right? So for example, if condition that the condition is not true, so the branch is not taken. If the branch is taken, then you usually jump somewhere else in the program memory, usually a little bit far away from the system. You can have forward branches or you can have backward branches, right? So you can jump backward or you can jump forward. So these are the main two things that you do. So this the first one is taken, and then of course some instructions are always taken. So for example, we have this jump instructions in RISC-V. It's called JAL, jump and link. That they're always taken. So if I see a jump and link, it's not the question of whether or not it's going to be taken. It's always taken. But remember that the processor does not necessarily know this, so we need to kind of know it. But there are some of them are conditional, right? So for example, branch equal, we're going to check the condition. If the condition is true, it will take the branch. If the condition is not true, it's not going to take the branch. So this is question number one, that the direction of the branch. Question number two is that if the branch is going to be taken, what is the new address? So the destination of the branch is also very critical for taking branches. For not taking branches, this is trivial because the next instruction is basically the next PC. But for taking branches, this is a very critical question to answer because let's say even I predict that it's taken. If I don't know what is the next instruction, then what's the point, right? So I need to know that. And there are a whole bunch of problems that you need to fix for that question as well. Important things before actually jumping into the algorithms is that you want to get performance out of the branch prediction, but you don't want to introduce correctness issues. So your branch predictor should always have a mechanism for recovery. So whatever we do, whatever optimization that we make, we always have a mechanism to 100% guarantee that you can actually run the correct sequence of instructions. Okay. Otherwise, if your branch prediction optimization end up in executing some instructions that they were not supposed to be executed, then you're going to run into correctness issues. That's a big no-no. Okay. But of course, you can have this power versus performance issue. So you can do a lot of works with your branch predictor, and that's fine as long as you get performance. But again, you cannot introduce correctness issues in this system. And the whole premise of branch predictors is this, that I already talked about, that we want to optimize for common case. That if 99% of the time I make the branch, decision about the branch prediction is correct, even if that requires a lot of power and all, that's still worth it because, that's the common case and we can make the common case as fast as possible. So if, for example, the recovery scenario for like a very complex branch is very, very complicated, as long as it happens very rarely, that's the price that we can afford. Okay, so that's the main premise of most of these branch predictors. All right, so let's actually dive deep into different branch predictors. So in order to understand why we need different kind of units within our branch predictors, you have to take a look at different control flow instructions. So essentially, you kind of like have 5 different types of control flow instructions in RISC-V in generally in any ISA. So first of all, you have conditional branches. This is the common branches that you're going to have: branch equal, branch not equal, and so on and so forth. Essentially, there are 2 non-possible number of fetch addresses. Either the branch is going to be taken and it's going to be jumped to a particular label, or the branch is not going to be taken. In that case, your PC is next PC. Do we know the direction at the fetch time? No. So you cannot statically kind of figure out what should we do with this branch because it's checking some conditions. Condition could be one time true. This next time may not be true, right? Then we have what we call unconditional branches. In RISC-V terminology, this is JAL and JAL-R, jump and link and jump and link register. So these are unconditional, means that the direction is always known, it's always taken, and great thing about them is that there's always one possible outcome, one possible address. Then we have a call and a return. Call and return are technically unconditional branches. Okay, so if you want to categorize them, it's essentially part of this unconditional. The reason that they kind of like spell them out differently is that call, the direction, both the call and return, the direction is always taken, but the address that the call goes to is only one address. That's the beginning of your function. But the return address could be any different address because you can return from any point in your system, right? So you can call a function at any point and you can return to any point of the system. So there is no one particular address that you can remember for the return. Sometimes I call this function from function A, sometimes I call it from function B. If I see a return, it's first time it has to return to function A, second time it has to return to function B, right? So for example, I have a function foo that's like this. At some point it has a return. The return should be back to wherever it's been called. So for example, let's say I have another function A, that somewhere in that function I call foo. So the first time I have to return here, but let's say if I have another function B, that also have some instruction and also call foo, then at that point it has to return here. So I can jump back to anywhere in the program if I want to with the return. And that makes the return very complicated instruction. It's easy to predict the direction, but it's very, very difficult to predict the target. Okay, so that's why for return, we usually have another mechanism. Then lastly, we have the most complex instruction for branches. These are indirect branches. Indirect branches are always taken, but their destination could be also anywhere. Why? Because these indirect branches are branches that are based on the address of the register. So usually it's like x1 and some immediate. So whatever the value of x1 is, this is the address that we're going to jump to plus the immediate. And then if I change the x1 value to another value next cycle, then I'm going to jump to somewhere else. So any sort of history of where did I jump to doesn't really help in most cases because that value can constantly change. Okay. An example of this is think about your switch cases, right? So your switch cases is a good example of this indirect branches or your function pointers. So these are all examples of this indirect branches. All right, so based on this different types of control flows, we're going to use a bunch of different components within our branch predictor. So essentially a branch predictor is a combination of all of this. So it's not just one, but there are a bunch of components. So what do we have? The main thing we have is the branch target buffer or BTB. Then in RISC-V, we have what we call a simple branch predictor or BIM. This is a bimodal predictor. Then most of the modern processor has this thing called return address stack or RAS. And then we usually have what we call a sophisticated predictor. Again, this is just the terminology of RISC-V and Boom Core. They call it backing predictor or BPD. Okay, so we have a BTB, BIM, RAS, and BPD. Okay, so don't be confused of what they are. We're gonna actually talk about them one by one. To put it in the perspective, your BTB, essentially your BIM and RAS is part of the BTB itself. Then you will have your BPD as a separate unit. And as you can see, the BPD is by far the most complex part of the system. It takes 4 cycles in our design. So what is the branch algorithm that we take? Again, this is basically just based on Boom. But again, Boom is just a representative of many high-end processors. So usually for branch predictors, you want to have first consult the next predictor. This is a very simple predictor that's kind of like works most of the time for, let's say, unconditional branches or for simple branches. Then if we are not really sure what we need to do, then we go with more sophisticated branches, okay? And of course, we consult branch predictor on every instruction. The whole thing is that some instructions are not branches, so we don't do anything and we move forward. But remember that when we are consulting the branch predictor, we don't know whether this is a branch instruction or not, because the way we do it is that we right away, we're gonna consult the branch to get as much speed as possible. So basically you're consulting the branch predictor for even like an add instruction technically, okay? So here's the algorithm that, we consult the next predictor, next line predictor or NLP. This is the default, which is combination of BTB, RAS, and BIM that we're going to talk about. And then for non-instructions, we just continue normally. But if you see that, well, we need a more sophisticated branch predictor, then we consult the backing predictor as well. Okay. And then, of course, all of these things needs to be updated in the background. So we make some decisions, we move forward with it. Hopefully we make a correct decision, so we don't need to recover, but we always need to update our branch predictors, because if it was a correct decision, we want to reinforce it, right? We want to say that, oh, this was a good prediction, continue making prediction in this direction. If you make a wrong decision, we want to tell the branch predictor that, oh, you made a wrong decision, learn from this mistakes, and next time give me the correct decision. So this dynamic update behavior is a very, very important aspect of a branch predictor. Okay, so how do we do the first simple one, the BTB one? So in RISC-V, in the boom core, a BTB is like a structure like this, that it has a bunch of rows and it has a bunch of columns. The rows is essentially these things. So we have a PC tag. This is the tag for the program counter. This is the value. This is the return. This is the jump. So these are basically vectors, 0, 1s. This is the ID that basically tells you which of those 4 instructions it is. And it's also, remember, the target address. This is the target address that we're going to use. So first of all, why do we need tags? Anyone?
See, we've done that instruction like that specific.
Yeah, so we want to see whether that is the same instruction as before or not. Remember, because we always consult the branch predictor for every instruction. So each branch instruction is different than the other branch instruction. So we need to defer them, right? So not the behavior of all the branches are the same. Some of the instructions are even not branches. So you want to be able to see what are you predicting. Because if it's an add instruction, you don't want to actually have any accidental matches, okay? So you need some form of a tag. So what do we store as a tag here? We usually store the entire PC as a tag, right? So the PC itself is the greatest indicator of which instruction this is, because each instruction has a unique PC. So you can store the entire thing here as a tag, okay? There are some other ways to make this smaller. So for example, what you can do is that instead of like storing the entire PC here, you can use some bits of PC for indexing this table. If I'm using the lower bits of PC, for example, for indexing this table, then I no longer need to store those because it's already used as the index. Then I use the rest. But it doesn't really save that significant amount, but generally just keep in mind that I need to somehow store and remember the entire PC. If I don't remember the entire PC, then I'm gonna make incorrect decisions accidentally, okay? Then what we do, so then essentially what we do is we're gonna do this thing. So if the match is found, okay, so if I get a PC and I see that I saw this PC before, this is all about, like, branches is all about history. That is like, what happens before, let's repeat it, okay? So that's the basic idea of any branch predictor. So if I saw this branch before, the first thing I'm going to check is whether or not this is a simple branch. What is a simple branch? The simplest branch that we can see is a return, because return is always taken, right? And return can be basically remembered based on the called return stack, because every call has a particular return, right? So we always go back to the latest call, right? So I can have this thing called return address stack. That essentially what I do is whenever I see a call, I immediately put the PC of the next instruction into my BTB and store. So I make this return equal to 1, and I put the target as piece at this address. Okay, so this is why we call it a stack, because it's kind of like pushing and popping, right? So whenever I see a call, I push the next instruction because that's where the return address should be, right? I push that instruction into my BTB and I save the PC and I save the address. Okay, that way, when I see the return, I'm going to see the tag going to be matched. I'm going to see that the return bit is equal to 1. Now I have the target, and then I can move forward. And this has 100% accuracy, 0% chance of misprediction, because you always know where your return of RAS is. Okay. The second thing that is also very simple is this unconditional branches. Okay. If it's an unconditional branch like a JAL, then I can also, like, if the PC matches, then it's 100% guarantees that we can jump to the correct address, because there's only one address, one and one address, right? So there's no problem with that. The problem is for the conditional branches, right? So for the conditional branches, we don't have the information here. So we need to consult the more sophisticated branch for the condition, okay? Again, for the condition, we can store the tag and we can store the target, because again, conditional branches only has one target. We don't know the direction. So what we do is that in parallel with BTB, we also consult our backing predictor. The backing predictor gonna give you the direction. The BTB gonna give you the target. So a combination of this will give you the branch. So if the BPD says that this branch is not taken, then I'm gonna discard this target address because I'm gonna continue. But if BTB says that, oh, this is taken, then I'm gonna take that target and then gonna continue. But again, since these are prediction, nothing is guaranteed. So there is an opportunity of mistakenly predict or not, take or not take the branch. Okay. But that's what we do for this design.
Do we
Okay.
not use the BIM? Because this uses the bimodal table for this.
Yes, so bimodal table, so the bimodal table in RISC-V terminology is just for unconditional branches. For unconditional branches, we have 0 and 1 basically. That's our bimodal.
So.
Yeah.
Right.
No, if you have. something
Okay,
to-
is the bimodal predictor not, that's BPD then, not the BIM? This is for conditional branches, we use the bimodal predictor.
Yeah. So this val here,
Uh-huh.
that's a bimodal predictor.
Okay.
So like if it's 1, it means that the branch is taken.
Taken.
If it's 0, it
Taken.
means that it's not. Yeah.
I'm still confused on how do you store the PC, like the PC value in the target when you get a return call? Like, so do you just assume when you have the call, the return, like the return PC value?
Yes, because
I mean like the actual line of the return, like the instruction.
yeah, so for example, let's say I have function A, okay? And then I have a bunch of instructions,
Yeah.
okay? And at some point I have call foo, okay? So what should be the return at? So let's say PC here is 0, this one is 4, this one is 8, this one is 12, this one is 16. I'll just go by 4 because instructions are 4 bytes.
Yeah.
So the next instruction is 20. What is the return address of this should be?
20.
It should be 20, right? So the moment I see this, here's what I'm going to remember is I'm going to put the 20 as the target address of this return instruction.
So you know where the return instruction is.
Yes.
Okay.
If you know it's PC, you just set it to next PC, which
Yeah.
is PC plus 4.
I know like the target value, but I just like which PC, like the tags where you assign it.
Oh yeah, you put that. So you don't technically you don't need to so if this is a stack, you don't even need to know the return. So here's what we're going to do. So think about it as a stack, right? Initially it's empty. When I see a call, I'm going to push 20.
Okay. Oh yeah.
Okay. So if a return comes without any other calls, what I'm going to pop from this is 20.
20.
If another call happens in foo, then I'm going to push another one, let's say another address here and another address here. Since always it's going to be like this, right? So you always return first. You're always going to read the correct value.
Okay.
So essentially there's like, so here, here, I'm not showing you like how we actually generate this tag, but there is like an internal push pop things that they basically use that for the PC. Yeah.
Just one quick question, within the BTB, the target is the RAS and the val is the bin?
Val is the bin, target is just the address that we're gonna jump. Yeah, it could be the return address, for example. Yeah.
And the val is obtained from the history of just the most recent.
For BTB, the val is very simple. Unconditional branch is always 1. Yeah.
And then like conditional, it's.
We don't know. Conditional is gonna be so this jump, none of these is gonna be 0. So like for unconditional, this jump bit would be equal to 1. That's why we take the target. If this jump and this return are all both zeros, this is a conditional branch. So we're gonna basically ignore these values. We're gonna consult the branch predictor.
Consult the val.
Yeah, but we're gonna take this target. We're gonna take the target, but whether or not choose those targets is to be determined by the predictor. Okay? Make sense? Cool. All right, so I think that's the place we're gonna stop. So last thing I want to say, this BIDX is the branch index. And basically, since we have 4 instructions at any given point, not all of them will be branched. So this one basically says which one is the branch that you are basically making your decision on. Okay? All right. So rest of this lecture will be recorded and posted on the website. Please watch it. And the moment you watch it, please start working on your CA because that will basically give you introduction. At the end of this lecture, I'm going to talk about how to start your CA as well. So watch this fully, then start your CA.